Welcome to linear and nonlinear patterns of change. Our objectives are to model and solve real-world problems involving patterns of change and to discover linear and nonlinear patterns of change using tables and graphs. Let's begin by looking at some key definitions that you will need. Function. Remember, we talked about a function. It's a relation where there is only one output for every input. So in other words, for every value of x, there can be only one value for y. We have a value or an input of 2, we can only have one output, say 3. We can't have 2 give us an output of 3 and 9, for example. Function rule. A function rule describes how to convert an input value. It's basically an equation. So we want to take the input value, put it in, and then we get an output value for a given function. Here's an example down here of a function rule. Y equals x squared plus 3. Remember, this is in function notation. F of x is the same thing as y. Nonlinear function. A nonlinear function is a function that does not form a line when you graph it. Think about this word, nonlinear. The word line is in this word nonlinear. Think about non, that means not. So it's not a line. Then we have linear function. That's a relation between two variables that when you graph it, it does form a straight line. Have you ever thought of a roller coaster? Let's consider that perhaps the speed of the roller coaster is a function of its height. So after doing some research, here's some data that was collected on different roller coasters. Three of them. The Timber Terror roller coaster, the Kingda Ka roller coaster, and the Top Thriller dragster roller coaster. So here we have the height and then the corresponding speed. So let's start by creating a table and determine if the information is linear or nonlinear. When we create our table, we usually put the independent variable here on the top and the dependent variable on the bottom. So based on this information, pause the video and fill out the table. We know that height affects speed. Speed is therefore a function of height. The faster we go is related to how high the roller coaster is. So speed depends upon our height. We could, if we wanted to use function notation, maybe we could call height little h, and we could call speed capital S of h. So is this information linear or nonlinear? Look at it for a while and see what you can come up with. While you were thinking, you might have pulled out your calculator and try to do something like this. Look at the difference between our x values and our y values. Well, you might have looked at the difference between 85 and 420 because you might have noticed that these are out of order, and then looked at the corresponding y value or speed differences. And you would look at this and not be able to maybe make sense of it. You wouldn't know if they were linear. What you would need to figure out is the average rate of change, which we will explore in a later video. In this situation, we might be able to help ourselves if we were to actually graph it. But we'll come back to this in a moment. Let's look first at some linear functions. They can allow us to represent real-world situations, and they can help us understand situations in which two pairs of values are related by some rule, like we talked about in the objectives. We can represent this problem with a function table, an equation, or a graph. Representing a problem in more than one way can sometimes help us understand how to solve it, as we saw in the previous problem. Let's look at this example. This table shows how the total cost of buying tomatoes changes depending on the number of pounds of tomatoes purchased. Let's examine the table. Over here in our x value column, we have the number of pounds purchased, which we'll call little p. And it goes up by 1 every time. We have 1 pound, then 2 pounds, 3 pounds, 4 pounds, 5 pounds. So we can just look at this difference as equal, going up by 1. Then we have total cost in dollars. So it's $2 for 1 pound, $4 for 2 pounds, $6 for 3 pounds, and what would you predict would be next? Well, if you're looking at the pattern, because everything goes up by the same increment on each side, we would probably then predict that this figure was going to be $8 and this one would then be 10. Now, let's look at A. Write an equation to describe the relationship between the pairs of values in the table. So how are we going to do that? Well, the first thing you might notice is that each t value here, so our y value, is greater than its corresponding x or p value. So whatever rule we have should involve either some sort of addition or multiplication because we're growing. Notice this goes up by 2 every time. Let's go ahead and consider addition first. Well, for each one increase here in our x value, our y value goes up by 2. So if it's going up by 2, what if we add 2? Or add 1. 1 plus 1 is 2, but 2 plus 1, that is not 4. 2 plus 2 is 4, but 3 plus 2 is not 5. So it doesn't really look like addition will work. What about multiplication? If we multiply 1 by 2, we do in fact get 2. So here we have 1 times 2 will give us 2. How about the next value? Now we have 2. If we multiply that by 2, we get 4, which is what we have. And we could continue on just to check to make sure this is a good rule. 3 times 2 is 6. 4 times 2 is 8. And 5 times 2 is 10. Notice that what we predicted here is really what this is, and it fits in our rule. So our rule is then to take the number of pounds, which is P, multiply that by 2, and we get the total cost in dollars, which is T. This is our rule. So we've taken what we found and we've turned it into a mathematical function. Now if we want to write it in function notation, we could write it as T of P is equal to 2P. We could also write this using our x and y variables. Total cost is y. It depends on how many pounds you have purchased. And so that equals 2 per pound, per every 1 pound. Now let's look at part B. Create a graph to represent the relationship between the number of pounds of tomatoes purchased, P, and the total cost, T. Well, here's our graph. The first thing we need to do is we need to provide labels. Well, what goes down here on the independent axes? Well, this is the number of pounds purchased, so this is our P. And then over here is our total cost in dollars, so this is T, or T of P. One way to graph this is just by plotting these points. So after 1 pound, it's $2. After 2 pounds, it's $4. And so on until I've plotted all these points. The next step then would be to draw a line. So I'm going to go ahead and connect these points with a line. Now remember that this line actually can go on and on forever, and it could actually go on and on forever down below as well. So based on this line, can we determine the cost of buying 6 pounds of tomatoes at the farmer's market? Well, if we look at this line, is this a linear pattern? And you should say yes, because our points form a straight line. When we have a straight line like this, it's very easy to make predictions. So if we were to buy 6 pounds, we know that we would be up here with our point, and we could probably say that if we follow this pattern, that it would be about $12. Now that you've seen how a table and an equation and a graph are all related and can help you to make predictions or solve problems, or even to determine if our function is linear, let's go back to our roller coaster problem to finish off. So here's our data and here's our table. And we were a little bit confused as to whether this was in fact a linear relationship. Well, look what happens when I graph it down here. Here's our first point here at 85 and 55. And then we have one over here, this next one, which is out of order at 420 and 120. And then right here at 456 and 128. Notice by graphing, we are able to determine that this is in fact not a linear function. These points do not form a straight line when we connect them. So this is how graphing can help us to determine if it's a linear function. We can also use tables and equations to help us as well. And this concludes our lesson today on linear and nonlinear patterns of change.